Okay, engineering students, welcome back. We are continuing in this series of looking at hydrocarbons, and today we want to wrap up on what we learned about alkenes, which is what we've been learning for the past probably 3 weeks. Yeah. So there's this structure which I've drawn here, which represents a one carbon alkene. It's got one carbon, so by now you know the name is methane. Yeah? And then there is the two carbon structure, 1, 2, and then each carbon has got 4 bonds. It's got 4 bonds. So this one is going to have it's going to have 2 carbons plus how many? 6 hydrogens. And we're saying that there is a general way of predicting the number of hydrogens if you are given the number of carbons. That if you're going to have n number of carbon atoms like n, where n is equals to 1, 2, for example, so that you can put a big capital C there, where n is the number of carbon atoms. So the number of hydrogens will be represented by, in bracket, 2n plus 2 in bracket, yeah? So that in this case you are going to say it has 2 carbon atoms, so n will be 2, so the number of hydrogen atoms will be 2 times 2 plus 2, so that will be 2 times 2, that is 4, plus 2, that is 6. So this will be what? C2H6. And that applies to all the hydrocarbons, yeah? I mean all the alkenes. Now, I want to okay. Before I leave the alkenes, I just wanted to show you, for example, it's something which I've showed you before, but it's good for me to show you. This is a 1 carbon alkene. Take the black ball as the carbon and the white ones as the hydrogens. So this is what you're going to be calling methane. As you can see, it is a tetrahedral, whichever I look at it, and the bond angles are 109.5. Now, for the 2 carbon, the one which I'm talking about here, this is how it exists in real life, yeah? So the black balls are carbons, and then the white balls are hydrogens, yeah? Okay, so this is 1, 2, 3 hydrogens, 1, 2, 3, so that is 6. So this is C2H6. And something which I want to mention, which I've not talked of before, is that the bond between the carbon is a single bond, and therefore that allows for free rotation, yeah, around the carbon-carbon single bond, yeah. There is free rotation. So this means that sometimes, if you are to look at maybe from this angle, yeah, so you can see there comes a time whereby these two can be aligned. Okay, let me just try to see what I can put. They can be aligned correctly like that. In this case, they are together, and then sometimes as it rotates, can you see how the structure is changing like that one? They are now overlapping. Now they are not overlapping. So there is free rotation, yeah, around the carbon-carbon single bond. That's what's going to be expected of alkenes. There is free rotation. They all have single bonds, so there is free rotation along the single bonds. Now I want to look at the next functional group, which I'm going to call an alkene. Alk for the number of carbon atoms, that's the prefix. Ene is the suffix. Just as we were saying for the alkane, the suffix was ane, or let me put a small a, ane. So it means that all alkanes, the name must end with ane. Now, alkenes have got something which you call double bond. So there is a carbon-carbon double bond. And this tells you that the simplest alkene, just as you cannot have a single carbon with a double bond, so you need to have 2 carbon atoms at least to have a double bond, yeah, between the between the carbons. So it means that the simplest alkene is going to have 2 carbon atoms. So there is no alkene with 1 carbon atom. The simplest alkene has 2 carbon atoms. So as we're saying, the name is going to end with E. So it means that for 2 carbon atoms, the name will be called, can you see well? Ethene. This one is called prop, and then butene. So it's butene, pentene. All the way is just shown here because it's going to be a lot of information. So there will be six carbon atoms will be hexene, 7 carbon atoms will be heptene, 8 carbon atoms, octene, 9 carbon atoms, nonene, 10 carbon atoms, decene. Yeah, I think it's something we'll be able to remember. So let me just try to see how I can just try to draw some of these this hydrocarbon. So if you're going to have like 2 carbon atoms, that will be the structure. If you're going to have 3 carbon atoms, you're going to get that will be then there will be a CH3. 1, 2, 3. If you have to look at this, if you have to look at this formula, what can you see? If M is the number of carbon atoms, if you're going to have 2, how many hydrogens are you having? 4. So it means that if C is the N, then the number of hydrogen atoms is actually only 2N, yeah? There is no 2. So like this one has got how many carbon atoms? 1, 2, 3. Yeah? So that tells you the number of hydrogens. It will be 3 plus 3, it will be 6. So there's something I need to show you. Okay. Look at this one. This is ethene. No, this is ethane. Ethane. That's an alkene, yeah? So let us look at ethane. Carbon double bond. So the one, can you see how the double bond though it's been shown like this one, but you know, in principle it's got linear bonds, but just being shown like this one for illustration. Now the thing is, this structure can lie flat on a plane. It's flat, and all the bond angles are 120 degrees. Yeah, take all the bond angles as 120 degrees. So this is the structure of what I'm calling ethene. Can you see it? I'm just showing it on this structure. So when I show it like this, and then you know I'm dealing with a structure which is flat, and this is how it looks like. Just keep it in your memory. This is how the structure looks like. Yeah, a picture is worth 1,000 words. I don't know whether the same applies to one image. Yeah, that when you see it, then you can be able to have as many thoughts about what I'm showing you, the way what cannot illustrate. Yeah, so just remember that's the structure of ethene. So in this case, so if it is propene, it means that I can what I'm doing is this. In this case, what I'm just going to do is probably remove one of that group, and then I attach what? I attach a methyl group. Yeah. So can you see? So this is the structure of propane. Look at the carbon atoms. 1, 2, 3. Can you see how it looks? Yeah. So the thing is, where there is the double bond, please note this. Where there is the double bond, there is no rotation. Yeah. The bond is rigid. But between my carbon here and my CH3, there is what? There is free rotation. Yeah. There is free rotation along the carbon single bond, but between the carbon double bond, there is no what? There is no rotation. Yeah, it is rigid. Yeah, can you see it is rigid? So the double bond is rigid. So that tells you that if you have groups around here, there's no way there will be rotation. But I think later I'm going to tell you later that it is possible to hit an alkene up to the point it's probably over 100 or 200 degrees, to the point to which the carbon-carbon bonds can actually break. It's called pyrolysis. Yeah, it's actually, you're actually breaking up the carbon-carbon bonds. Yeah, you can give it the bond energy. You can overcome the bond energy. You're going to get dissociation. Yeah, to which the bonds are going to fragment, and from there they can actually change to some other form. This is what happens in the oil industry, to which you get your crude gas, and then you're going to hear there's something called cracking. Yeah, a process called cracking, to which you've got a very long hydrocarbons, to which they are put under high temperature, to which the carbon bonds, they break down. Yeah, you're going to see what they can actually break down to. So this is my structure of what I'm calling my thing. Can you see how it looks like? There's the carbon-carbon double bond, and then there is a methyl group. So this means that if I'm going to have something like butene, it means that I'm going to have what? So I'm going to have a CH2, and then I'm going to have a CH3. Yeah. By now you also know that if I'm going to have this is equivalent to H. Okay. All right. So you can see this structure. Okay. So this is what? Propene, and this is butane. But then there is something I want to show you, that that when you're going to have butane, it is possible to have the double bond being at a second position. So this is how many carbon atoms? 1, 2, 3, 4. So this is C4. So it means that the hydrogens are how many? According to this formula, 8. 3, 5, 8, plus 3, 8. Yeah, C4H8. What I'm saying is this: it is possible to have the double bond at another position. Yeah, to also get a butane. For example, I can have a CH3 here. I can have another. Okay, let me put it another way. Yeah? Sorry. Can you see that? That is how many? 1, 2, 3, 4. The hydrogens are 1, 2, 3, 4, 5, 6, 7, 8. This is also C4H8. Okay? So this is also butane. What you're going to say is that this is an isomer of this. I mean of butane. So there are two isomers of butane. But later you're going to see that there can also be another isomer. For example, given the fact that this bond cannot change, for example, there is another isomer for this one, and this is if I've got to have my carbon, hydrogen, and another one down. Can you see that? Is it clear? So it means that along the double bond, this CH3 or the methyl group is top, this other one is down. In this case, both this CH3 which I've circled here and the one which I've circled here, they are on the same side. In this case, this methyl group and this methyl group, they are on opposite sides. Can you see that? So this is another isomer. So you can see that there are 3 isomers of butane. Yeah? Can you see that? There are what? 3 isomers of butane. Yeah? So the thing is, when we be coming to the name of the alkene, you're going to see that, hey, after 3 carbon atoms, whereby you're dealing with 4 carbon atoms, you need to indicate the position of the double bond. For example, in this case, we are going to see that we number alkenes starting now from the position of the double bond, the position of the carbon, the position of the chain nearest to the double bond. So this means that, hey, here there is the double bond. So it means that I cannot start this one as carbon number 1. I'm going to say, hey, number 1 will be this one. If I've got to have my blueprint back, I can call it on 1, 2, 3, and 4, position 4. Can you see that? In this case, whichever way I start, the double bond, where it is starting is on carbon number 2. If I start from here, 1, 2, 3, 4, the double bond is on between carbon number 2 and carbon number 3. So usually indicate the first position at which the double bond occurs. So if for example, in this case, if the double bond is between carbon number 1 and carbon number 2, you say the double bond is on carbon number 1. You indicate the first position. In this case, the double bond is between carbon number 2 and 3. So you say the double bond is on carbon number 2. Are you going to see that? If you say a double bond on carbon number 1, you are saying that the double bond is between carbon number 1 and carbon number 2. In this case, the double bond is between carbon number 2 and number 3. So you can say the double bond is on carbon number 2. So that tells you that if you are to give it a name, for example, if you are to distinguish between this structure and this structure, this one, okay, let me put it in red. This one will be called a 1-alkene. A 1-alkene, it says you've got a double bond on carbon number 1. So this will be called a 2-alkene, yeah? But now, we'll now not call it just an alkene like that, because an alkene is just a general name. You're just going to indicate what the alkyl group is. In this case, the alkyl group comes from the fact that you have 1, 2, 3, 4. So this will be called a what? 1-butene. Have you seen how we've come up with the name 1-butene? And this will be called what? You're simply going to change your alk to but, yeah? Okay? So this will be called what? 2-butene. This is called 1-butene. This is 2-butane. In this case, you're saying the double bond is between carbon number 2 and carbon number 3. This one, the double bond is between carbon number 1 and carbon number 2. All right? Okay. So I think I will. Okay, let me talk something about this this form of illustration which I'm calling isomers of this 2-butane. Let me mention something. So I'm just going to delete this side. Okay. So this is what I had. I have what I'm calling 2-butane, yeah? So what I'm having is now what I want to say is this, is that by now you know this one you can show it as CH3, yeah? So this structure you can show it like, you can simplify to that. And similarly, if you have this structure, you can say it is equivalent to CH3 okay, So that's what you're going to have. Now, so these ones which have now circled in blue are said to be isomers or regioisomers. So it means that, or they are stereoisomers. It means that they are isomers that have got the same number of carbon atoms, but they're differing in the way the atoms are oriented in space, region. Yeah, the way the atoms are oriented in space in various regions. So they're called regioisomers. Now, I want to show you. So let me take my CH3 as my red ball. So this is my CH3 and this is another CH3. Though you know I can show it a methyl group, but that will complicate what I'm just trying to show you. Yeah? What I'm saying is this: is that I can just try to put something like a methyl group complicated here like that, and then I attach another one, and therefore and then I attach another one there. The structure is going to look a little bit complicated, but what I want you to focus on is around this area. So just assume this complex methyl group is just a simple what? Red ball, yeah? That this is a methyl group, this is a methyl group, yeah? So what can you see here? This structure cannot twist. So if you are going to have your double bond, what can you see here? You've got your double bond, and then the hydrogens, they are across the double bond. Can you see here? There's the double bond, and then there is one hydrogen on this side, and the other one is on this other side. Let me show you the other isomer. Yeah, can you see the other isomer? In this case, here is your double bond, and then the two hydrogens, they are on the same side. They are on the same side of the double bond. Can you see here? Okay, let me move a little bit here. The two hydrogens, they are on the same side. And in this case, the two hydrogens, they are across, yeah? Across the double bond. This is on the same side of the double bond. So you're going to see there is terminology, there's a term which has been developed to show if you're going to have hydrogens being on the same side and the hydrogens being on opposite side. So if they are on the same side like this one, you're going to say this, you're going to use the word cis, yeah? C-I-S. C-I-S to say hydrogens, they are on the same side. So this will be called cis, you're going to call it cis butene, yeah? Okay? Now, that is a new terminology that has been developed to show hydrogens, they are on the same side. And then if they are across, scientists decided to use a word which common people are common scientists, or let me say common scientists, they or people know in day-to-day life, and they use the word trans. Trans means across. When they hear transatlantic or whatever, there's some even some matatus, they use the word trans and whatever, it just means across, yeah? Across means, trans means across, yeah? So trans is across. So if you're going to have two hydrogens being on opposite sides, that will be called trans. So this will be called trans, and then you put dash butene. Have you seen that? That is trans-butene. This is cis-butene. All right? Now, so for okay, there is some literature which which I give you access via the Google Docs on the reference document. If you're going to look at the section on alkenes, you're going to see that extract of the textbook is showing that the alkenes that are available in nature have got two hydrogens across the double bonds, and most of those which are available in nature are available as cis alkenes. Yeah, the ones which are normally the ones which are available. Excuse me. Majority of the alkenes in nature, especially the ones which are found in the food that we take, they contain the double bond being across. That is something I'm going to explain later when you're going to be dealing with the last functional group, which you're going to call carboxylic acid. Yeah, when you're going to be dealing with carboxylic acids, then you're going to see, hey, there's some carboxylic acids that contain double bond, and they contain very long chain, and those carboxylic acids, they are found in what you call fatty tissues in the body. So the scientists just call them fatty acids. It's just fatty carboxylic acids, but they're just called fatty. It means that they are carboxylic acids which are found in acids, and they contain what? They contain double bonds. So you're going to hear that word like trans fats and the cis fats. What it means is that the cis fats, they contain the double bond on the same side, which is what is said to be healthy fatty acid. But that one you're going to come to it later. You're going to come to that one later. The fats, that the carboxylic acid which are found in fats, which are called fatty acids, and they contain double bonds. Then the ones which are available in nature, mostly the ones which are healthy, they contain the double bond on the same side. It's called cis fatty acids, yeah, or the cis fats, yeah. So, but the point which I'm trying to drive at is that this position of the double bond, either being across or on the same side, matters biologically. Matters. It is very, very significant. So you need to know the difference between a cis alkene and a trans alkene. It matters in nature, biologically in nature, especially for you who are studying, who are biosystems engineering. You'll use these terminologies on and on again. Yeah. So there's the cis alkene, there's the trans alkene. Yeah. So I want to take a break now. It's approaching close to past. I want to take a short break, and then when we come back, I want to show you another type of isomerism when you're dealing with an alkene. I want to mention another type of isomerism, yeah, when you're dealing with alkene. Yeah, it's just like expanding the term of either the cis or the trans alkene into a more general alkene. So we're just going to take a break, and then I'm going to proceed from there. All right? Okay.